So good afternoon, all of you, and welcome to the first day, first session of GIAN course. As you all have scheduled with you, the first lecture will be delivered by Dr. T. I request Dr. T to present his lecture.
Okay, so should I start?
Yes, sir, you can. Sir,
Okay,
make
thank
it
you.
PPT form.
Okay. Okay, so thank you all. This is our first lecture on spatial analysis and water resources modeling and management. If I'm not very audible, let me know so that I can increase the volume or increase, change the microphone.
No, sir, you are audible, clearly audible, and your voice is also very clear.
Okay, thank you so much. The first things first, if you have any questions anytime, please use your microphone and ask so that it will be more interactive. I can try to answer it then and then. If the question requires more time, we can always use the break time or some other time later to answer your question. So let me start. So first of all, I'd like to thank GIAN and all the team at SVNIT for organizing this particular course. The materials, what I have collected are from different sources, including my publications, journal articles, and so on. I would request that you use the material in case if you're using in future for academic purposes only. And then if you need any more materials, you can always send me an email. Some of the figures are not yet published, so be careful with them. And please do not post any material online in any form because some of the figures are borrowed from copyrighted books of mine, so the publishers will have some issues when they find the materials online. So please let me know if you need anything, then we can request the publisher for providing the permission. So let's talk about spatial hydrology and analysis of hydroclimatic data. That's our first 1 hour, 1 hour, 15 minutes lecture. Of course, there's a lot of things to cover, so we have to go through very quickly. We talked about the processes, we talked about the objectives of this course, but the first thing you have to see is that the scale on which we are looking at different processes. So again, depending upon what type of process you're trying to understand, what is your ultimate objective for modeling, prediction, or operation, that will affect what type of scale you are looking at. So the floods can happen anywhere from minutes to longer period durations. Rainfalls can happen in a very small time period. At the same time, they can also happen over large areas. So the space-time continuum in this case is very different for different processes. So we need to make sure that we understand that we collect the data, whatever is required for our objectives. Now, in case of spatial hydrology, we are always working with either lumped or distributed models. Lumped models parameterize on an average for the whole basin or a catchment or a hydrological reference unit or hydrologically similar basins or a sub-basin and so on. So any type of spatial element you take in hydrology, we can lump the parameters, we can lump the inputs on such scale. The distributed models obviously require you to discretize the domain so that you have to understand the spatial variability as well as heterogeneity of your inputs. There's also a need for understanding the spatial variation of the inputs. That's pretty important for us because nowadays we are working with distributed hydrologic models as we move into the new era of explosion of the data as well as computational resources. So lumped models are still being used in many parts of the world, including United States. We use them for hydrologic design and so on. But however, whenever there is a chance for us to use distributed models, for example, in flood modeling, more and more distributed hydrologic models are used. regional simulation models are used, and so on. So in that case, we need to characterize the spatial variability. We do have point and gridded data sets that are available. So one thing we have to understand is that gridded data sets are either directly made from satellite or other sources, or sometimes they will be interpolated based on the point sources. So we do have two types of simulations which we use. One is the event-based simulation, where we are restricting ourselves to only one event or one major event that can influence our design. The second one is the continuous simulation models, which are basically evaluating the status of the system as the time progresses, and then we are looking at all the hydrological variables. Some of the variables may not be interesting to us, but at the same time, we want that continuous progression of our inputs as well as the parameters, as well as the processes as the time progresses, so that we can understand what is going on. Now, if you see in event-based models, precipitation becomes a very important input, because that we are looking at very small, tiny time scales, so precipitation becomes very important. Whereas in case of continuous simulation models, we have precipitation, soil moisture, and others drives the occurrences of floods. Okay, so this is important because sometimes we neglect soil moisture. That is one of the important components in many case studies in the United States and so on, that accurate estimation of soil moisture has become a very important factor for predicting floods into the future, at least a couple of days with a good lead time. So we do have different types of spatial data. We need to understand that spatial data is very important for our modeling purposes. We collect data in different pre-specified locations. We may have point or gridded data. And depending upon what type of data we are looking at, there are three different properties we need to understand. One is the support, the extent, and the spacing. So I'm going to define them a little later, but basically every data set will have three different properties which we need to be aware of. Gridded data is often generated by interpolation or images not from the point sensors. So when I say interpolation, mostly spatial interpolation. Obviously, gridded data has some kind of a fixed grid structure, or tessellation, if you want to call in spatial analyst terms or spatial analysis terms. Spatial data can be collected at regular intervals, and sometimes they are not. Depending upon what type of sampling strategies we use, how do we sample the data, how do we get the data from a field, from a basin or a watershed, that can be random, stratified random, uniform, cluster, and others. Of course, we have to be careful with the sampling bias, because sometimes we may sample more in one particular location than the others. Spatial data may be correlated depending upon what type of processes we are looking at. So spatial data also may follow Tobler's first law of geography, which is very beneficial for us, because everything is related to everything else, but near things are more related to distant things. So Tobler really helps to understand the process, or at least characterize the process of spatial dependency. That means when you collect parameters, they are linked with other parameters in space, because there is a spatial dependency exists. Now, the siting of the instrument is critical. And then homogeneity issues, if you are collecting the data over a long period of time, if you change your instrument, or if you were to change something else about the instrumentation process, then homogeneity issues will come back. So data is also collected in space and time, collection at different intervals in space at same time, or collection of the collection at different points in space at different time intervals. Sometimes chronological pairing is possible. Sometimes chronological pairing is not possible. When I say chronological pairing, that means basically you have time series having the exact same timestamp, so that we can use that information for validation or checking the data points, because you have data from another site which has the exact time matching. Sometimes serial correlation is possible depending upon the process you are looking at. That is, the series autocorrelated against itself. And then sometimes cross correlation is also possible. That means you have data from one site being correlated with the other side. For example, if you're talking about floods, the upstream station and a downstream station, when you're measuring stages, they may be very highly correlated. Okay, so but the stage in one particular stream may not be correlated that well with another stage in another stream located in the watershed. So again, cross correlations are possible, and serial correlation or persistence or autocorrelation is possible. Point data, of course, we collect a lot of data, including soil moisture. We calculate, we observe evapotranspiration data, and so on. These are all point data sets. The most common point data set is our rain gauge data set. Okay, we collect at an instrument site. Typically, the support, which I'm going to discuss very soon, will vary depending upon the variable measured. Point data sets are prone to random and systematic errors, outliers, anomalies, and missing data. And gridded data also will have issues related to outliers and anomalies and errors. But again, because gridded data is generally generated using point data, so we might not encounter these problems very often in case of gridded data. We also need quality assurance and quality control. Variability of the processes can be captured in a region if the network is dense and uniformly distributed. So there's also a lot of research where the optimum networks are developed. We use information from the processes as well as the limited amount of data we have already collected, and we try to optimize the monitoring networks. The extremes may be or may not be recorded. At the bottom, I'm showing different types of rain gauges. The tipping bucket is the most by far common rain gauge used in the world. Of course, it has its own problems, both systematic and random errors. Weighing type, float type, and standard type. Standard type is manual rain gauges where an observer goes every day in the morning, picks up the rainfall amount, they do the corrections for evaporation or any other issues, and then they report the data. So it happens every day at a specific time. But of course, we are now in the process of eliminating standard rain gauges. We are going for more automated rain gauges like tipping bucket and so on. Now, when it comes to gridded data, we are looking at data which is available at a fixed spatial resolution. We call it as tessellation. These estimates for this gridded data are obtained from point observations using spatial interpolation schemes. So once we have this data, then we can talk about the grid or pixel size matters, because that helps in defining our resolution for our hydrologic simulation models. Gridded precipitation data and temperature products are now available for all over the world. You can get at different resolutions that can be used for different modeling purposes. The advantage of gridded data is that they help us to understand the spatial variability of the process. Of course, distributed models will enjoy the gridded data. They would like to have as much as gridded data as possible because spatial variability of a process is captured very well. Although there are some issues with the gridded data. First of all, the main issue is that sometimes the variance is deflated. That means you don't get the variability what you see in your point data sets, so that is deflated. So that you need to take care of by using what we call bias corrections. Then you have what we call underestimation of the higher end values and overestimation of lower end values. So this is also very critical because whenever you are using spatial interpolation models, they tend to overestimate the underestimate the higher ends and overestimate the lower end extremes. So that is the main problem with our spatial interpolation models. So what are we doing now? Now the new methodology being applied in many parts of the world is that instead of working with low amount of data and trying to develop models like theory-based models or conceptual models, trying to understand the dimensional homogeneity of those models, trying to make sure that they are validated with a small amount of data. But now what we are doing is we're trying to come up with what we call process-guided data science models. Now we have a lot of data. Let the data help us to understand the process much better. Let the data also help us to define equations, functional relationships between the variables. And once we have that, then we can go back and validate the dimensional homogeneity of those functional relationships and make sure that we are having a relationship that is physically acceptable. So we are basically taking the entire amount of data, trying to develop these relationships, and then going back to the theory-based models, which we really intend to develop, which will stand the test of time and valid for all combinations of situations. So what we are doing now, we are taking care of deep learning, artificial intelligence techniques, and so on that can help us to get those relationships. Sometimes you might say that the black box models, like what we call the ANNs, the artificial neural networks or deep learning models, they may not provide a lot. But then once you have the data, you establish the model, then you have some idea about the functional relationships between the variables, which can be ultimately used to develop the relationships what we want. So in essence, the black box models are more or less helping us to develop what we call the white box models, where we are able to see the relationships, where we are trying to understand more about the process. One thing you need to understand is that we have this model complexity where there are simpler models and there are more complex models. When I say complex models, doesn't mean they are computationally intractable. You can still run on the regular personal computing environment, but then the complexity comes from what we call the model structure as well as the parameters. On the other hand, you also have what we call the data availability. So if you have small amount of data and small model or medium model complexity, your performance will be average, it will be good. But then if you have a large complexity in your model and small amount of data, then the problem is the parameter estimation. Sometimes you might get a number of values which are equally good, and then it's very difficult to take which parameter set that will help for your particular region. So again, the performance measures which we use will affect what type of models we select based on the data what we have and based on the model complexity. So what we do in that situation, we do spatial data analysis that will help us to understand what type of data we have. Then we combine the time and we call it as separable space-time data analysis, in the sense that we take a time slice and then do a spatial analysis, or we take a region and we do a time-based analysis, or sometimes we combine both of them and we call it as space-time data analysis. So these days we are getting data from different sources, and most of the data in the United States and Europe, or many parts of the advanced developed world, we get data from telemetry. So therefore, the manual measurements are going away. We are not doing any manual measurements. For example, in case of river discharges, we don't measure the discharges, but we measure the stage, which is common everywhere in the world. Now we are using advanced sensors so that we can capture the stage measurements. Precipitation measurements are common by using recording type like our tipping bucket, which helps us to understand the variation of the rainfall with respect to time. And then the data transfer is having through telemetry, so that there's no need for a manual observation or somebody going there to evaluate the data sets. We also have the gridded data sets. Then we call the precipitation estimates. These are not observations or measurements. These are estimates, I call them, because these are the surrogate measures of your precipitation. And these come from radar data, or sometimes they come from satellite data, even though we have not perfected satellite data to estimate rainfall for smaller regions. For large regions where there are no networks, we can still get precipitation data. Then we have what we call the gridded data sets, which are developed using these kind of estimates. So there should be a difference between measurements and estimates, and we call them as quantitative precipitation estimates, or QPEs. And these are used for all kinds of purposes in the United States and everywhere, for both real-time forecasting of floods, real-time forecasting of flash floods, short-term forecasting of floods, and so on. So this is an example of a telemetry. You are measuring data, and then the data is automatically transferred to the data recorder, and the data recorder sends the data to a satellite, and then the satellite provides that to a provisional data office, and you download it. So you can see that the whole process is automated now, and that will help us in quick digitization of the data. And then initially it's called as a provisional data, where they try to understand the problems with the data, remove anomalies and outliers, and then make sure that it is quality controlled, and then post that data to all the agencies who can use the data for operational management as well as other decisions. So in case of spatial hydrology, especially distributed hydrologic modeling, we need spatial analysis. And spatial analysis is required for both preparation and processing of inputs for hydrologic simulation models, especially distributed hydrologic models. We use GIS. GIS is the Geographical Information System-based software. And then we need to geoprocess the data which is available to us, and also both hydrometeorological and climatological data. We also process vector and raster data. Vector, we know the representations can be point, polygon, and areas, whereas raster data sets are gridded data sets which have a fixed grid size or tessellation, so that we can do all kinds of operations on them, including matrix algebra or raster algebra on them, so that we can derive whatever required inputs for our distributed hydrologic models. So again, once we have the point data, we still need some kind of conceptually simple or computationally intensive geostatistical approaches or spatial interpolation approaches may be required, because that will help us to define our gridded data sets. So, as I said in the beginning, precipitation becomes a very important input to our models, and that's why I'll focus this session on a little bit on the precipitation part of it, because that really helps us to define our flood estimates correctly. Of course, there are other important parameters like soil moisture, the amount of soil moisture that is available. The base flows are an important part of the flood forecasting process. We also need to know the time of concentration of your basins. We also need to know the shape and other aspects, topography, drainage density, network, and other things. But then most of the studies, when they have found out when we really want to have accurate predictions of our hydrographs, we need to adequately characterize our rainfall inputs. And this is no-brainer, because this is whole idea of what we call the GIGO concept, that is garbage in, garbage out. So if you are putting a wrong value of precipitation, obviously you will not be able to simulate the conditions in the field, or especially attain those peak discharges, which are very critical for our flooding scenarios. So the main interpretation here is that, can we call a model, what type of model? A robust model. A model which provides reasonable, acceptable, defensible results that are expected for an application, considering a small deviations in your input structures or inputs and parameters. Model can handle input data uncertainty. The main uncertainty for our lumped or distributed hydrologic models is the input data uncertainty, because if we give a slightly changed soil moisture value, the whole forecast or the prediction or the simulation will result in a completely different value of peak discharge or the hydrograph itself. So therefore, data uncertainty is very critical for us for making both real-time, short-term forecasts for floods. And then, of course, the model should be able to handle reductions in the spatial and temporal sampling. If you can make it more coarser, the model will still work in a distributed domain. It is resistant to changes in the different forms of inputs. For example, you might provide observations sometimes to your model, sometimes you can provide estimates. So that indicates that, are you able to simulate the conditions when you interchange these two? Okay, so Robust design, basically what we call the hydrologic design or flood frequency analysis for our design purposes or generation of a maximum possible flood. In that case, are we able to address the issues when we have lack of data? Okay, and can this design be adaptive in the sense that when you change the system, like what we have here, we are able to see the evolution of the climate. Are you going to have what we call an adaptive design? So we know that precipitation has the strongest causal influence, not casual, but causal influence on our hydrologic response. And spatial patterns and space-time variability is extremely critical, okay? And then we need to see how observations and estimates will work and how we can move from point measurements to point measurement to grid estimate, so that we can move from lumped models to distributed models. And then the scale triplet, as I was telling you, the support, extent, those are important when we are talking about the gridded data set. So here's the scale triplet. This is very important when we are talking about measurement, okay? Now, I talked about forest versus tree in the sense, do you look at the minor details within your sampling, within your observations, or would you look at the whole region? So therefore, if you see here, the spacing is the first one, where the spacing between the two measurements. The other one is the extent, the whole region. The support itself is the whole instrument measurement area. For example, if you take a rain gauge, the rain gauge typically has an 8-inch diameter. So in that case, the support becomes 8 inches, okay? So when you have these three important components which help us to understand how we are sampling, that really helps us how, when we define the gridded data, how it's going to affect our data sets. So sometimes we do upscaling and downscaling. Upscaling is basically taking point measurements to a more coarser gridded structure. And downscaling will be going from a particular grid structure to a finer grid structure. Sometimes we'll use auxiliary variables, sometimes we don't use auxiliary variables. Auxiliary variables are other variables other than the variable of interest. For example, if you're interpolating precipitation, the auxiliary variables can be location of a particular region, closer to a mountain, closer to an elevated area, closer to a sea or an ocean or a water body. So that can help us to define our precipitation interpolation much better because we have that extra information. So as I said, spacing, extent, and support, if you change those things, things will be different for your spatial variability. For example, if the spacing is too big, the small scale variability is lost. So you just get some kind of noise. There's no pattern in your observations. Extent, if it is small, then what happens is that sometimes you miss the large scale pattern. Support, if it is too large, small scale variability is smoothened out. So again, all these things are very critical when you are trying to make the observations which might be helpful for your models. Sometimes you don't have a lot of control on them. For example, support, you have the instrument, which is the standard instrument, so you don't have much control. Extent and spacing can have a lot of control that can help us to define what you're doing. So here again, moving from lump to distributed. In case of lump, you have one value for the whole watershed or a basin, and you move from to a distributed model where we are using what, let's say, for example, QPE, that is quantitative precipitation estimates. So the spacing becomes constant, extent becomes again the same as what we are looking at. Sometimes it's bigger. The support is always constant because we are talking about a grid. So there is a transformation from lump to distributed when you do the scale triplet. Now, what are we doing about rain gauges? Some time back, there was a talk that maybe we don't need rain gauges in future because we have radar-based precipitation estimates that are available now. So, and of course, we have what we call drisdometers. Drisdometers used in many parts of the US to find out the drop size distribution of the rainfall so that we can characterize the rainfall better. but of course they are very expensive. They are mainly used for applied research purposes. But then, can we consider rain gauge observations as ground truth or not? Sometimes that's a valid question, because the truth, what we get from rain gauges is also uncertain, because there are systematic and random errors. So what we do is we combine different data sets. We call it as multi-sensor precipitation estimates. We do rain gauge, we take radar, and then we take satellite sometimes. We combine all of them and then provide an estimate. Once we get an estimate, we try to do the bias corrections. Even though you have combined in the best possible way, there are some errors which are probably systematic errors. There can be a bias in the data where we need to correct. We will do the corrections. So quantitative precipitation estimates are available in the United States. We have a number of radar installations like weather surveillance radars. We have a lot of data for that, and we can develop gridded data of specific tessellation. And once we have that, we can get the radar data for our applications. So here's a way how radar measures and how satellite measures. For example, radar looks into the upper atmosphere, slightly above the horizon, and then start measuring the reflectivity of the signals which are received from the raindrops. And then we use that reflectivity to convert into rainfall measurements using a power relationship. And that basically is a very simple power relationship. Reflectivity is equal to A R to the power B, where R is the intensity. So if you know the reflectivity value, you can easily convert that into rainfall intensity. Satellite looks at a different level for the whole process. And then, of course, rain gauges, as in the bottom, which are included, may or may not capture the precipitation which is falling at a specific location. So definitely radar provides an advantage of getting that comprehensive estimates, which can help us in capitalizing the spatial variability of the rainfall better. So are the rain gauges really ground truth? Of course, we have to ask that question. There are errors, there are sparse networks, there are missing data and outliers. We sometimes miss the extremes. And sometimes rain gauge as a ground truth is really questionable. Okay, is an example of missing records, an outlier, and an anomaly is which blends into the data, but it's really not visible for us. We think it is a really correct observation, but not, because the observation is constant. So that indicates it's an anomaly. So we have to go through a number of QA/QC procedures to make sure that the data is correct. So anytime you're putting precipitation in your models, there is uncertainty, right? So we can take care of that using quality assurance and quality control, or sometimes some people use the rainfall itself has some kind of a multiplier so that they can use it as a calibration. Okay. Now, of course, it's not a good idea. We cannot use that, because that can create all kinds of problems, especially when you're trying to calibrate the models. Now, the question is, can we calibrate with measured precipitation or QPEs or vice versa? So how well the models perform if you are using observations or if you're using estimates, okay? Sometimes if the precipitation is bad, we might remove that particular time period in our models, but that's a questionable modeling exercise. We cannot do that. So I'll briefly talk about radar-based precipitation estimates, because that's very important now for India also. If you see, this is the most recent news about Indian weather radars. So this was in I think in July of last year, but there's also articles recently coming in talking about weather radars, how they are useful for predicting the rainfall amounts, and then also tracking the different hurricanes you have in different parts of the country. So, of course, there are some radars which are not working very well in India. Some of them are being calibrated, but in future, there is a good number of radars that are being added within India. So soon, you will be using radar-based precipitation for running your simulation models, running your distributed hydrologic models and so on. So obviously, it's better to have some idea about how radar works and what kind of issues radar will have. Anybody interested in trying to look at radar-based rainfall estimation? There's a book we have edited. I have multiple chapters in it, and we worked on a task committee for a long period of time, and then this was result of that work. And this book is really useful for professionals as well as researchers who are just starting to understand how to use radar data, or how to understand the jargon around radar data, and how radar data can be obtained from different agencies, and how you can actually take the radar reflectivity data, which is coming out from your weather radar centers within India, and then how you can convert that into rainfall estimate. It might be a very interesting exercise for people who might be interested in doing research in this area, especially for the Indian radars. Are they able to capture the rainfall variability better than any other radars in the world? So there are a number of things we have worked on in the last several years, almost 10 years or more. And then you can see that we are looking at using radar data for missing data estimation, development of radar-based precipitation networks or optimum rain gauge networks, correction of biases, developing framework for tools for radar-based precipitation data products so that we can evaluate, we can identify outliers and anomalies and so on. So there are a lot of work we have done, and the type of radars we have in US are mostly S-band. These one have a range of 230 kilometers. They are very powerful radars, very expensive. India also has some radars which are on exactly the same band. They're called S-band radars. There are also X-band and C-band radars which have a shorter distance-wise, but they are stronger in getting the spatial variability because there is no reduction in the signal when you're using shorter band radars. There are some issues with estimating rainfall using radar. So you can see that we can see the drop size distribution within an area which is about to provide precipitation. We also look at the concentration, the number of drops. Sometimes we will have different forms of precipitation, hail or snow or some other forms. And then finally, we may have issues with other types of alien objects within the clouds or within the area where it is raining, and that might create problems associated with estimation. For example, flies or birds or some other type of dust particles which might affect or give a feeling that there's a tremendous amount of rain happening in a region when it is not happening. So typically what we do, you might have seen a radar installation. There's in Chennai and Delhi. So you have this big dome within which an antenna is there. And then it basically looks into the upper level of the atmosphere, slightly above the horizon, 0.5 degrees, and it goes up. It scans the entire cloud to get the reflectivity, and that results in a map like this. So for example, at the bottom, you see that this is a Florida map where there's a Miami. We have a radar at that location, and that's 230 kilometers. That helps us to understand what is going on. So this is the color coding, which can help us to find out what is the reflectivity value. They are expressed in decibels of reflectivity. So to make it smaller so that we can estimate the rainfall value. Sometimes if you have a large mountains or obstacles or buildings that may block the radar beam, because radar is basically sending electromagnetic signals and trying to get the reflected signals. So based on the reflector strength, we can estimate the rainfall. Okay, so we will have issues with sampling limitation where we are estimating the data. And of course, we'll also have issues related to the height at which we are measuring the rainfall. So because the whole vertical cloud is used for estimating the rainfall. So a number of things can happen. For example, if the radar radome looks like a football, so if this is already wet, maybe you'll register more reflectivity because the signals are also getting reflected from that. Sometimes you'll have corrections for that. And sometimes your radar recognizes rain, but there's no rain gauge registered at the rain gauge because the water has not been observed by the rain gauge. Or sometimes you don't see any rain in the horizon, but by the time it reaches the rain gauge, you'll have some rainfall. So again, there are a number of issues. There can be evaporation below the beam, what we are looking at, or there can be winds below the beam, which shows that there is not amount of rainfall because we are using rain gauge measurements. So there are a number of errors, but with all these errors, radar data is really good now because you can get a correlation up to 0.9 or 0.95 without any bias correction. So that indicates that we are able to do a very good job. We have radars in the United States. We call it as dual polar radars. These radars can differentiate between a fly and a raindrop. So that means they're very high resolution radars that can really help us to understand the rainfall amount. So there can be issues, attenuation, that is reduction in the signals, systematic errors. If you're using a wrong relationship between the reflectivity and rainfall intensity due to unknown DSD. DSD is nothing but drop size distribution. So if you're using a wrong relationship, you might end up with a completely different rainfall. Okay, and then of course different types of events. Sometimes you'll have convective rainfall events. You have what you call frontal systems or cyclonic systems, which bring different types of rainfall. Okay, so emerging QPEs, that is the qualitative precipitation estimates, nothing but radar-based data. These are, as I said, becoming better and better. We are having dual polar radars now, and there are some gaps. They can also help us to filling missing data. So here are the locations of all the 190 odd radar locations. Each one will cost around $10 million. And most of the country is covered because if you look at the range of these radars, 230 kilometers. So that means there are some gaps in some parts of the country, but still they cover very well in most of the inhabited regions, in the cities and towns. So that really helps us to understand the rainfall variability. Now, this is very critical because all this information is given to river forecast centers. There are multiple river forecast centers, and these people use this information to produce what we call real-time forecast for the rivers, real-time and short-term forecast for the rivers, both medium and long-range projections for what might happen for the river floods in different parts of the country. So the basic idea is very simple. You have this reflectivity values coming in, and then this changes every time when the antenna rotates. So you have different polar coordinate systems every time. So you need to find out where your gauge is located so that we can do the corrections. So we use spatial analysis, and then we extract the polygons. We do temporal integration, and then finally get the best parameters for the reflectivity rainfall relationship, and then finally produce what we call the quantitative precipitation estimates. These are some screens of that, how we extract the data, how we process the data. This one was done long time back ago, and then of course things have changed a lot. We also use optimization to find out the best coefficients for the ZR relationship. If you type in Google, we probably will discuss in the tutorials also. It's called the reflectivity rainfall relationship. This is the same relationship used all over the world. The only thing is A and B values will change in that power relationship. And sometimes we use optimization to find out the best values of ZR. Very simple. We use the power relationship. I was telling you that this power relationship, A and B, these are the two parameters we need to estimate. And then depending upon what type of event we have, we can do the best values of ZR. We can also change with respect to season. We can also change with respect to month. We can also change with respect to a specific type of event. Now, I told you DBZ, these are the colors which are reflected, given to us. It is nothing but 10 log 10Z. So that's what is called the decibels of reflectivity. Okay, so we can come up with different ZR relationships, reflectivity, rainfall relationships, and sometimes using an umbrella application of ZR can lead to some errors. So here are some of the values which have been documented by several researchers. Some of them can be useful for India if you are working with the Indian radars. For example, there's a one for Chennai, 101.3. This was done by Raghavan. There's a nice book by Raghavan for radar meteorology, if you're interested. Very interesting book. Depending upon the type of storms, convective or stratified thunderstorms and so on, the A and B values will be different. The question is that how do we improve the ZR relationship? There can be a number of questions. Now remember, we are always using rain gauge as a ground truth. If you are using rain gauge, which we have to make sure that the rain gauge data is also correct. Okay, so we can also improve ZR relationship by using what we call moving window approach or a constant window approach or seasonal approach, so that we can come up with the best ZR values for a location. So this needs to be estimated for every location wherever you are trying to estimate the rainfall. So here's an example at the bottom where we are trying to optimize the ZR relationships and then get the best values of the precipitation. And here's an example of the absolute error that is being plotted. And you can see that we are able to improve the absolute error by optimizing the ZR relationship. The blue one is the optimized ZR, but the red one is the original ZR. So before we do the bias correction, we need to go through all the checks related to our rain gauge data. We do all kinds of checks. These are beyond our scope of this particular lecture, but we do checks so that we do what we call the ground truth evaluation and correction. Here's a nice example of a Japanese meteorological agency providing information about the data. This is very important. And what they do is they evaluate the data and then provide qualitative expressions for the data quality. So, for example, reliable, quasi-reliable, incomplete, missing, and then they also tell us if the site has been moved, so that also helps us in establishing the homogeneity of the data sets. So we need to quality control the rain gauge data. That is very important. Sometimes you'll have missing values. You need to take care of that. And sometimes you might have outliers in your rain gauge data sets. You need to go back and look at those things. So once you have the point data, which we call it as ground truth, we need to take care of all the outliers and anomalies. And if there are any gaps in the data, we need to take care of that. And these gaps may be because of systematic and random errors. So there are a number of reasons why we get underestimation and overestimation, and you can see that there's so many reasons. These are available in any standard publications of WMO. And some of the things that might happen is physically impossible values, constant values, values about a pre-specified threshold. Sometimes they can be rare extremes. If you have 15 inches of rainfall in 5 minutes, that's a lot of rain. So 15 inches is what? 15 times 25.4 millimeters. That's a lot of rain in 15 minutes. So maybe it's not real. So you got to be careful as an outlier. And improbable zero values, unusually low values, unusually high values, and then of course gaps. So there are a number of methods you can identify this thing initially when you're doing a quality control of your rain gauge data. Standard statistical methods to rule-based methods where we write rules. And then, of course, we'll have data mining-based methods like clustering or neighborhood-based methods. And then, of course, we can use radar data and other data to find out problems with the rain. So anytime we are talking about data, there are three things that are possible. There are unknown unknowns, there are known unknowns, there are unknown unknowns. Known knowns are observed data. Known unknowns, because we know that there are missing data. And unknown unknowns, basically saying that we don't know the mechanisms by which we are missing the data. A number of methods have been produced by different researchers. I also worked on imputation of missing data, that is estimation of missing data. We developed a software that can help us to estimate missing data. And here are some of the works which revolve around estimation of missing data. And you can try to find out some of them which might be useful for your region, or methods which are conceptually simple that can be applied for your regions. Now, sometimes we resort to spatial interpolation, not temporal interpolation, especially when you're looking at precipitation data. Precipitation data happens in pulses, so therefore there is very low autocorrelation. So you cannot do temporal interpolation. So therefore you have to always use what we call spatial interpolation. You can see here, these are the statistically significant lines, and you can see most of the autocorrelations fall within these two lines. For an example data that shows that there is no autocorrelation, so you need to proceed with what we call spatial interpolation. Sometimes you can do temporal interpolation using last observation carry forward or base observation carry forward. Those are not the best approaches, but you have to always do spatial interpolation. So we can also do quality control based on available data sets. Whether we say if there's any problem with the rain gauges, we can go back and look at the other nearby rain gauges to say that whether there is actually rain or not. If not, we can always replace it. If there's no rain at a location, we can always change the value and then replace it. But sometimes we may be overestimating the lower end values, that is zeros, or we may be underestimating the higher end values, those are extremes. So these are some of the cases. So the bias corrections, anytime you are developing a gridded data set, that is radar data set for your distributed hydrologic models, or if you are developing a precipitation gridded data set for your distributed hydrologic models, you still need to do what we call bias corrections. That means your gridded data set may be either overestimating the values or underestimating the values, so you need to correct them. So in this case, for example, you can do either local or global correction. So these are your sites, that is rain gauges. The gridded centers are located. So you can do some kind of a distance-based correction, like this one here, where I'm using inverse of the distance, or you can use exponential distance method to correct each of these grid values so that you can do bias corrections. Sometimes you can do additive correction. You take the rain gauge and you subtract from the available radar information, and then you propagate the errors. Or you can do what we call mean field bias correction. That means you take the GR ratio, gauge to radar values, you take the mean of it, and then if you get a factor, you multiply every single value so that you can estimate you can correct the grid data, that is by what we call bias corrections. And sometimes you can do bias corrections based on a single rain gauge in your grid, or multiple rain gauges around the grid, and also several grids, which we call the Queen's contiguity. So you can go around the grid and then find out if there are rain gauges, and then you can do what we call the corrections. So all this will help us to improve the gridded data set, because when gridded data set is initially developed, so we might have some issues related to the bias. So we need to always correct them. So here's an example of bias corrections in one of the sites in Florida, and you can see that the correlation coefficients before and after using CDF plots, and you can see that the correlation coefficients have a lower non-exceedance probability after the correction, so that indicates that they have improved. Similarly, the reverse happens in absolute error, things have happened, and you can see the original and the bias corrected. So you can see how the bias correction can improve the spatial variability after you already have the gridded data. So you have to go through the process of bias correction. In many parts of the world, we still use lumped models. When you are using lumped models, we have to get what we call mean areal precipitation. So hydrological design, we still use what you call mean areal precipitation. And we also rely on PMPs, that is a probable maximum precipitation. And these are sometimes difficult to get, and sometimes the rain gauges are not measuring them. So the emerging QPEs, that is the quantitative precipitation estimates, are helping us to get that best values for our lumped precipitation models. The MAP is very important for the success of lumped models, and sometimes MAP is also used in semi-distributed hydrologic models. And what we do is we can use point measurements, or we can convert point measurements to gridded data and then finally calculate MAP. So remember, PMP is very important, the probable maximum precipitation, because that will generate what we call the probable maximum flood, PMF, and that can be useful for our design purposes. And these days, because radar is available to characterize the precipitation very well, we are able to generate what we call PMF. Okay. Sometimes the radar data is not available for a longer period of time as opposed to the historical rain gauge data. So we may have probably 10 years of quality radar data. Some agencies have accepted that. They said, okay, 9 years of data is acceptable for using for the lump modeling based designs. So how do we approach MAP? We can objectively partitioning the area or weighing schemes, but of course we need to do both calibration and validation. And how do we do the MAP estimation? We can use the QPEs, we can use radar only or satellite only, or radar with gauge, satellite with gauge, and so on. But of course, if you are using gauge, you need to make sure that they are reliable estimates. And point data can be easily transferred to fields. Fields mean surfaces. So for example, either you can use a weighing method to estimate the mean aerial precipitation, or first go through the spatial interpolation method, generate the gridded data set, then finally get the mean aerial precipitation. Or you could take the radar data set, which is already coming as a gridded data set, and then you can do some bias corrections. Once we get the bias corrected gridded data, then we can do mean aerial precipitation. Both are possible. So what are some procedures for our mean aerial precipitation? Quickly, we have a number of methods. Decent polygons, everybody knows, or Voronoi polygons, and then centroidal distance method, isohycal, and line methods. Then we have triangular methods, two-axis methods, nearest or natural neighbor methods. All these methods will really provide some kind of arbitrary weighing schemes to penetrate aerial precipitation. Then I said we can take the point data and then generate them into a form of surfaces, and then from surfaces we can estimate the mean aerial precipitation. We can use kriging, or we can use trend surface models. Again, depending upon what type of model that characterizes the rainfall spatial variability in that area, that will help. We can do that. These days, the Titian polygons are now generated using radar data. For example, these are radon polygon method. This is by two researchers from South Korea and Japan, and they have come up with exactly using radar data to divide them into polygons based on the rainfall that was occurring. So in that case, they're kind of matching with the Thyssen polygon. So that indicates that radar data can be used to develop the whole idea of area weighting or area-based average estimation, similar to Thyssen polygons, as long as they match very well with your rain gauge data, which of course they will match because radar is able to get the spatial variability. Sometimes we also have grid transformations. Depending upon what type of grids of data you have, we have to do spatial transformations. Depending upon that, we will get the orientation. For example, sometimes the grids are oriented in a different way, so we need to get a Cartesian grid. We can do that by using weighing schemes, either using the maximum area as a weight, or the partial area which is covered in each of these grids can be used. Again, we can decide whether we want to do local or global. Local is fixing a certain number of neighbors. Global is, again, using all the neighbors within the system. Both can be done. So there are several MAP estimation methods. MAP is still used for lumped models for design. And the final topic is to validate the QPEs. Anytime when you have the quantitative precipitation estimates, how do you validate them? How do you say that they are reasonable for your distributed hydrologic models? Because we are interested in generating the floods or simulating the hydrographs. We need to understand how much we can trust this data. Okay, so a number of questions can be asked. What is the quality of the data? Are the radar and rain gauge data characteristics similar? What is the overall bias? What is the error structure? So a number of questions can be asked, because depending upon what type of modeling exercise you are doing, you can ask whether your rain gauge data and radar data are similar statistically. Are they able to produce a similar rainfall amount? Are they able to produce a similar dry and wet spells? All kinds of things can be asked. And of course, we need some kind of framework to assess that. Okay. We can also assess the quality of the radar data by checking the hydrological response. So what I would do is I'll take the radar data, put it in my hydrologic model, and then see how well it is able to capture the characteristics of the discharge hydrograph. If it is doing a very good job, then I can have some trust on my in my radar data. Okay, so there are two things. One is the hydrological response-based evaluation. The other one is non-hydrological response-based evaluation. Now, one thing you have to be very careful when you're comparing rain gauge to radar. There is a mismatch between the size. You know, rain gauge is very small compared to radar grid, so you are kind of unfair comparison there. But sometimes people do generate gridded data from point gauges and then try to compare with the radar data. That is also possible. So how do we generate what we call reference QPE? That means the final ultimate QPE which can be used for our distributed hydrologic models. First, we take all rain gauges, we divide them into two sets of ground truth. This is one ground truth, this is another ground truth. If you see here, they are a combination. This whole gauges is a combination of this and this. And then first you take the radar-based data, you do the bias corrections, you generate the QPE, that is your calibration phase. Then for the validation, you use the other set of rain gauges and you check everything, and then finally validate the data, and you get to the point of what we call the reference QPE or RQPE. Okay, let's do some comparisons between rain gauge data and radar data. There's a comprehensive framework we have developed. This is a paper in 2017 in AC Journal of Hydrologic Engineering. If you're interested, you can look at that. And I'm going to show you some comparisons. This is a little bit about the data, the type of comparisons we can do: temporal, spatial, event, or point. We can do visual, quantitative, and statistical. As you can see, so many error measures we can use. We can use statistical methods. We can use visual assessments. And all these assessments will help us to understand the radar better. Okay, we can also use skill scores. Skill scores are mostly used in forecast verification technologies or forecast verification approaches. We can use them. We can use a Taylor diagram, which can help us to understand multiple models at the same time. We can use association plots. We can use transition probabilities to understand the dry and wet spells. We can use variograms to understand spatial variability. We can do kernel density estimates to understand the characteristics of the distribution. Then we can do some hypothesis tests to understand if the two distributions, rain gauge and radar, have the similar probability distributions. So first we do is we can come up with the contingency measures, which are very common in many assessment studies, both in hydrology, hydrometeorology, and forecast verification literature. So all you have to do is do the rain and non-rain precipitation counts, so that we can talk about error rate, sensitivity, probability of detection, probability of false detection, which are very common. You can find in any hydrometeorological research papers. And based on that, there are different skill scores developed by different researchers. We can use them to find out what will be our skill, whether when we are using the radar data compared to rain gauge data. Then the transition probability, given a wet condition, what is the probability of getting into a dry condition, and the reverse, and so on. So 4 combinations are possible. This is a one step ahead what we call Markov chain. That means one step ahead dependency. You can also do a two-step ahead dependency also. Then we can do what we call linear error in probability space, where we try to find out the two precipitation values. One is coming from radar, one is coming from rain gauge, and see how close they are by looking in the probability space as opposed to the regular values. Of course, you need a CDF of the rain gauge to get those values. We can actually compare histograms. There are so many measures that are available, both real and binary measures are available. We can find out whether the histograms are similar. This is the Taylor diagram I was indicating, which can help us to understand multiple models at the same time. Then we can do what we call resampling. We call bootstrap sampling. We take the rain gauge data and the radar data. We repeatedly sample so that we can establish the confidence intervals. Then we can do what we call replacement tests. That means we take some portion of the rain gauge data and fill it with radar data to see if we are doing a good job when we are filling with the radar data. Cumulative mass curves, as you know from your basic hydrology textbooks, we can be done. Then we can do mass curves between two different data sets we can understand. And mass curves with respect to time can be done. Variograms are basically the difference in the two values squared with respect to distance. And you can check how the variability is captured by two data sets. You can do different summary statistics. You can do serial autocorrelation, whether the rain gauge data persistence and the radar data persistence are exactly similar or close. Then we can do different tests to see if both of them come from the same distribution or not. For example, two-sample Kolmogorov-Smirnov test and so on. Then we can check the error measures. If you have multiple products, you can check for error measures. We can also check the Nash-Shuckley efficiency criteria. You can check different correlations. And we can also check the errors, because we want to make sure that there's no issues with the radar data as the time progresses. So that means there's no error structure with respect to time, there's no heteroscedasticity, that is the non-constant variance and so on. And we can check the normality of the residuals and so on. So all the tests we do for some kind of linear regression, we do the same thing for your. Then we can compare the kernel density estimates. These are nothing but the smoothened histograms. So just to quickly, the example of rain gauge and radar data sets, we have 3 different radar data sets, near real time, end of the day, end of the month, and 2 rain gauge products. We can do comparisons between rain gauge and radar. We have 190 rain gauges in that region, and we can do different combinations of the tests. So we also develop a bias assessment tool so that we can understand whether there's a bias in the rain gauge data. So when we look at the bias, that is G by R ratio, that is the gauge to radar ratio, most of the time it is close to 1, but there's some spread in different years. That indicates that there is a lot to be done to improve the radar data. These are the cumulative distribution functions, and the scatter plots. Of course, they look very bad, but it's a very small resolution of 15 minutes. This is for your annual data. Annual totals at different gauges. The box plots give a better closeness. The correlation coefficients for different years between radar and rain gauges. Things are improving. As you can see, there is a negative skew a little bit, even though they are normal, but more correlations are on the higher side. The quantile plots are improving as we move from year 1 to year 4. So that also indicates that the radar technology is improving as we move from first year to the 4th year. The transition probabilities, there are underestimation for wet to dry for radar and wet to wet transition overestimation for the radar. So this is mainly because the radar looks into the upper atmosphere, whereas rain gauge is on the ground. So their collections or their switches from wet to dry or wet to dry or dry to dry, those conditions are different. So obviously we want to do a better job of this. Distribution similarity is improving. This is the number of sites which are failing, as you can see. As you go towards the 4th year, things are improving. Autocorrelation structure is good, replication wise. There's no structure in the errors in the residuals, so that indicates there's no heteroscedasticity. There's no autocorrelation of the residual itself. That's also a good sign. There are some spatial bias issues. The red point indicate higher bias, so we need to address that. There are some regions where the bias is much higher, so we need to go ahead and see what is the problem, why radar is overestimating or underestimating. The Taylor diagram gives us all the three models, end of the day, month, and near real time. And we want this stem to be very close to here so that the reductions will happen in the errors. But most of them have a correlation of 0.8 to 0.95. The correlations are also improving as we do the corrections. The variance is a problem. The radar is underestimating. As you can see, the gray dots are radar and the black dots are rain. So the variance is underestimated, which is the main problem with the radar because it is not looking at what is happening at the ground, but this is the problem which we can address through some bias corrections. Some of the indices can be used for short-term operations and planning purposes for different water management agencies, even for flood control and modeling. So the final thoughts are the new developments in QPE are now challenging the attitudes of hydrologic modelers who are firmly confined to use of rain gauge data for calibration testing. Nowadays, we are seeing that QPEs are used for many things, not only for hydrologic model calibrations and usage in distributed hydrologic models, of course, but then for lumped hydrologic models also we are using radar-based QPEs, that is quantitative precipitation estimates. We do have variance deflation, we know that, underestimation and overestimation. But then the spatially varying grid rates are very useful. Finally, just a quick note on how do we test if the radar data is much better than the rain gauge data for our hydrologic response. That means we put them through the model and see how well we are doing. Now, in this case, we are seeing that we can apply Alan Turing's imitation game. For example, you have a person sitting here at sea. On the other side of the screen, there's a computer and a person. So this person asks a question. So if both of them will respond, if this person C cannot distinguish between whether the answer has come from a computer or a person, then the computer has passed the intelligence test. So similarly, we can try that in hydrologic modeling. For example, we have the ground truth, we have the rain gauges, we put the QPEs, we put through the hydrologic simulation model, we calibrate the parameters, we get the parameters. The other one is ground truth, bias corrections, bias corrected QP. So this is not bias corrected, but this is bias corrected. And then you can see if the parameters are same or not. That's one thing. The second one is you are not doing any bias correction, and then you are directly putting through the system. The same thing here. That's why we call it as uncorrected QPE. The other one is we get the ground truth, we get the spatial interpolation, we get the gridded QPE. We don't do bias correction. We send it through hydrologic modeling simulation. We get the best parameters. And then we see how well is our forecast. We do the same thing with the other one. We do the bias corrections. Again, we get the best value of the forecast. The other one is to see if we avoid the bias correction completely and then see how well we get the estimates of our discharges. The other test we can do is transferability of the parameters. The first one is, sorry.
Sorry to interrupt you, sir. Shall we stop here and continue at 6:45 p.m.?
Two more. We are done. Two more slides.
Other speaker has already arrived.
Sorry, 2 more slides. We are done. Okay.
Okay, sir. Okay, sir.
Yeah. So we can check the parameters if they are different or not based on the exercise we have done. And then based on the optimal knowledge, if you have the parameters, whether they are matching with the radar data. So at the end of the day, the two problems we have is equifinality and multifinality. That means we can have the same response for the same starting point. That is, dissimilar initial conditions may lead to similar end state, or similar initial conditions may lead to completely dissimilar end state. So this is based on the calibration process. So we have to blame it on that. Okay. So that's the end of the whole idea of using quantitative precipitation estimates. That's becoming common now. Now that you have radars in India, that will be the next step for you to use for distributed hydrologic models in the next decade or so, once the radars are perfected and so on. But of course, you are also developing gridded precipitation products using rain gauges. So we'll have a tutorial session later on. If you have any bunch of questions on this lecture, we can always address them when we go to the tutorial session. Okay. Sorry, I had to stop here. And
thank you very much, sir. And definitely there are few questions which we'll discuss in our second session, which will start at 6:45 p.m. As per India timing.
6:45. Okay, thank you.
It's already 5:30, so 6:45 we will start the last session. So dear participants, I hope you enjoyed the first day, first session. And now we have speaker, Dr. Rajiv Mehti. So as I have introduced during the inaugural session, Dr. Rajiv Mehti, Associate Professor, Hamburg Fellow, Germany, Boycast Fellow, India, USA. His area of interest, hydroclimatology and water resources engineering, watershed development. His specific research interest areas are hydroclimatic teleconnections, modeling for climate change impact assessment, analysis of hydroclimatic extremes, sea level rise, statistical methods, remote sensing application in hydrology, artificial intelligence, and machine learning. He is Fellow of Royal Meteorological Society of UK. He has published number of books, 12 number of book chapters. He is having 1 patent and copyright. He has published around 80 referred journal papers and 68 conference and symposia reports. He has published 7 technical reports and undertaken number of research projects as well as consultancy project. So I request Dr. Rajiv Mehti to proceed with his presentation. Sir, you can share your screen.
Yeah. So
sorry for the delay.
Yeah, no problem at all. Can I please confirm I'm audible clearly to all of you?
Yes, sir, you are audible clearly.
Yeah. So thank you very much, Professor Yadav, for first of all for inviting me, and secondly for such introduction. And just for the audience, I'm just recovered from COVID positive, which I'm still not able to in the sense not supposed to attend the office, but still it is permitting. So I'm here. So this one is really a great honor to be in this gathering and all this that GIAN course, and I'll try to take some time to give some introduction and some application, which is basically on the a statistical tool called Qpes. So is my screen shared?
Yes, sir.
Yeah. Fine. So as you can see, that title of my talk is the Introduction to Qpes and its application to the hydrologic analysis under climate change. Where you know that in the line of the GIAN course that you are attending, it is the spatial analysis. So this, when we talk about the hydrologic analysis, I was just attending the last part of the Professor Ramesh he was just presenting. It's a very interesting and very nice talk, and I'll just want to give you maybe some part where some of the modeling strategies, some of the modeling criteria, some of the modeling tool that is being utilized, and there are several such, and Coppola is one of them, which has already established is highly potential in different fields like say frequency analysis, multivariate modeling, simulation, prediction, those kind of things. So the basic thing is that in many of the spatial as well as temporal analysis, we need to know the joint distribution between multiple variables. That's the key thing in many of the analysis, whether it is temporal as well as for the spatial. Now, Coppola tools, it basically helps us to find out that joint distribution if we know the marginal distribution of different variables. Now, how we'll proceed about this particular talk, it has two major parts. In the first part, I'll try to give an overall introduction of the background theory, and then I'll take you to the second part where some of the applications, some of the recent studies in the area of hydrology and hydroclimatology that has been taken up. So how to basically a demonstration of that particular methodology. So as you can understand that this first part is basically little bit mathematical, and I hope that that should not be too much boring of this mathematical part. As you know that some of the background things, some of the background mathematical concept must be clear in any of the theories. It is not that one for this particular area only. Even for the AI/ML that we have heard very recently in this as a potential application. So this background concept and logic, those things has to be understood. So what you see in this one, there is a book on the statistical methods in hydrology and hydroclimatology. I'm taking most of the part from the last chapter of this book authored by me, which is the second edition is also available now. So at the very starting, when we talk about the copula, it basically originating from a Latin word. It's called the copulare. So that copulare, the English meaning is to join together. So as I mentioned at the starting, that there are multiple variables that we need to know what is the joint distribution. If we know their marginal distribution, of course. So these functions, they helps us to know the joint probability distribution between two or more random variable. So as you know from already your whatever the background in the statistics or probability methods that you have. So in case of when we talk about the two variables, we are calling it as a bivariate. When it is more than two, we call it as a multivariate. Analysis are but most of the demonstration initially what we will do in this particular part, we'll take two variables first and then try to extend it for the further dimensions, which we generally call it as a n copula, but that is of course as a at a later stage. Now one more term that we should know before we proceed first is called the scale-free measures of association. So what is the scale-free measures of association is that many of the times, particularly as you know, most often we utilize the correlation coefficient. Those are not basically the scale-free. The scale-free means it is irrespective of their underlying distribution, underlying probability distribution. What is the association between two random variables? So those are called, I'll just demonstrate one of them, of course, which is popularly known as the Kendall's tau. There, the association between these random variables and their marginal distribution, if these two informations are known, then we can utilize the functions called copula. It is generally designated by the letter C, and again it has a copula density function as well as the copula distribution. Both in case of the density we use the lowercase c, and for the distribution we use the uppercase. So it is a function. So that's the first point. It's a function that couples or joins the one-dimensional marginal distribution of multiple random variables to their joint distribution function. In other words, there are different other things are also there. For example, the distribution function. So copula is a distribution function indeed, whose one-dimensional margins are uniform. Now, what does this one-dimensional margins are uniform means? That so if I have one random variable, I feed one marginal distribution, I reduce it to its reduced variate, that varies from 0 to 1, so that becomes the uniform. So its one-dimensional margins are uniform. So it is true irrespective of the marginal distribution. That means when I couple them, when I join them to get that joint distribution, it does not. So it is applicable irrespective of what type of marginal distribution that the original random variable they have. Here is one sketch. Again, it is for the bivariate case. Suppose that there are two random variables are there, x and y. So as I told that if I know their marginal distribution, I can reduce it, and this effects of this variable x, which can lie between 0 and 1. Similarly, another random variable y that also can lie between 0 and 1. Now, any point in this is basically a pair of the x and y. Now, if I have their joint distribution also, which I can designate as a function called h, then for any such pair, that pair for this joint distribution will correspond to a point again between 0 and 1, because these are all the distribution function that we are talking about. Now, these 2 points, as you can see here, they have a functional relationship between these two. And this functional relationship is basically can be modeled through different copulas. So this correspondent indeed is a function, and this function is known as the copula. So now again, as I was mentioning, so this is for just for the visual interpretation. I just put it for a two-dimensional case or a bivariate case. So you can imagine now for another dimension, if you have another variable z, which is of course orthogonal to the previous two, so you can get an unit cube, and any point at inside that unit cube will again correspond to one point on this their joint distribution between the three random variables. So it is basically the concept is similar for the higher and higher dimension. Sorry. So graphically, as I have mentioned, that only two dimensional copulas can be shown as a surface in the three-dimensional space or as a contour diagram here. So you can see here, so this is basically this surface, the colored surface, as you can see, it is from the blue to red. So red means the higher value. So this is the C, U, V. So U and V are the two random variables are there. So the copula function that we are talking about, it is a surface here. Again, these things varies from 0 to 1, and this joint distribution also varies from 0 to 1. So here it is a very specific thing that CUV is UV, and which varies between 0 and 1. So this is the complete definition of the function. It is later on we'll understand that this is called the independent copula, and there are some properties for the function to support before I can say that it is a copula function or not. So this is just one of them. So this is the three-dimensional representation of it. Or what we can do, we can present the same surface in a contour plot also in the right-hand side that you can see. So it basically shows that what are the their values for a particular contour. In this way, it can be shown. So as I mentioned that there are some properties for a function to be satisfied before we can say that this is a copula. The first thing is that domain of the copula is I power n. So it is the nth dimension, and I is for the unit space where this I is 0 to 1. As you can understand that these numbers vary between 0 and 1, and it can be n dimensional. So the just previous slide I showed you one case which is I 2, so two-dimensional case, but it can be for any n, but where each and every dimension is basically from 0 to 1. The next one, the property 2, there are two points are mentioned here. One is called grounded, another one is called 2 increasing. So these are the properties of this function. I will explain it graphically. That will be better in the next slide. Before that, for every this the copula function, if one of the variable is equals to 1, for example cu1, that means v is equals to 1 here and u is equals to 1 here, in any of this case, if one of them is 1, the value of this function becomes u itself, the other one itself. So c1v is equals to v, and c u1 is equals to u. Now this last one, if you just check in case of this one, so if you just put v equals to 1, then the function is u, and if you put u equals to 1, and then the function is equals to v. So this is also, so this is just one example I'm showing. I'll show you the some more values, then it will be more clear. Now here, that grounded and two increasing that I was mentioning. So let us take up this two increasing function first. A two-dimensional analog of this non-decreasing function. As you know, for the univariate probability distribution function, when we talk about, it is always a non-decreasing function starting from 0 to 1. And that analogy, if we just take it to the cupola function, it is called the two increasing function. How is it assured? That each volume of one rectangle B, which rectangle I will just show you, it should be non-negative. That means greater than or equal to 0. And it is true for all the rectangles B whose vertices lies within that 0 to 1 range. So now say that there are two random variables are there, x-axis and y-axis. This is one rectangle, and that rectangle I am showing it here, where you can see that it is on the base, and this is the cupola function that you can show. Now if I just take the values at these four corners, that means just I take a slice of this surface here and showing the values at four corners, x1 y1, x2 y1, x2 y2, and x1 y2, then the edge volume means the value of the function at the maximum point, that is x2 y2 minus x2 y1 minus x1 y2 plus this x1 y1. So if you see what I have done, it is basically I have taken out the area up to this line, and the total area that forms this one, and you will see in this process that twice this area will be deducted. That means one time I have to add it. It is basically, if you see from a volume point of view, it is just you are cutting the cake from these four lines, and there is a volume of the cake over this rectangle. That means it should never be negative. So that's what the edge volume of this rectangle B that stands for. So here in this case, this should be always, there will be some volume must be there and should not be negative. That's why it is the analogy. So that from here, from this point, if we just start towards the maximum, so if it is increasing, then of course the value of this function, the cupola function, is also higher and higher if we just go towards from the, so here you can say the x2 is greater than x1 and y2 is greater than y1. This is number one. And secondly, as I told, that is a grounded, and grounded means here you can see that this first one of the variable, if it is 0, then the value of the function itself is 0, and that is what is called grounded. So these two properties, if I just put it here in mathematically, it looks like this. So the one of them, so uv here, v equals to 0, and here sorry, this would be u equals to 0, then the function itself turns to be 0. Another, this property I already told, that is if one of them is 1, the value of the function is u and v itself. And last one, that is if u1, u2, and v1, v2 in the I in such that u2 is greater than u1 and v2 is greater than v1, then this one, that is u2 v2 minus u2 v1 minus u1 v2 plus this u1 v1, it should be greater than or equal to 0. So this last property is called the two increasing, and the first one is called the grounded. Additionally, this is one of the property which is the basic properties of a cupola. Here it is, example is shown for the two-dimensional cases, that is I2, and these are the properties. There are one more property also we know, which is called the Frederick-Webding bounds. That means any function or any surface that we are talking about, it is bounded by two surfaces. One of the surface, the pictorial representation is shown here. One of this one, it is basically on the ground up to this diagonal and then straight going towards this corner. This is the lower bound. An upper bound is that it's just like a two side of a pyramid. So any cupola function that we talk about should lie in between these two bounds. Okay, so that's why it is basically the lower bound is shown as this W and upper bound is shown as this M. So these are the two bounds for any function. Here is one small example, working example, that is just check whether this is a valid cupola function or not. This we have already shown in the pictorial one, that is a CUV equals to U into V. Now, if I just put those properties now, just take 4 points, U1, U2, and V1, V2, so that U1 is less than U2 and V1 is less than V2. So we have to prove that this one is positive. So these values I can just put from this function here, and then if I just put that U2 is U1 plus D, and D is of course some positive number, since we have already defined that this is greater than this, then we can show some calculation and show that this value, this entire value is a positive value. So it is supporting the property of this 2 increasing function, number one. Number two is it is grounded. This is one of them is 0, then function itself will be 0. So that's why it is a 2 increasing, and this is grounded. So then again, if I just put one of them equals to 1, then it is reducing to the value of the other one. Hence, we can say that CUV is a valid cupola function. Whereas the second one, it is a U square plus V square by 2. If we just put this one, that is one of the property, that is whether it is grounded or not. If I just put one of them equals to 0, which is not equal to 0, the function doesn't become 0. So once any one of the properties is violated, we can say that it is not a valid cupola function. So this, how this UV looks like, this is a pictorial representation of this. And it is also later on you will know that it is called the independent cupola. There is one very popular theorem based on which the entire this theory is utilized. It is called the Scalar Theorem, where this joint distribution of 2 random variable can be obtained by any cupola function through their marginal distributions. So conversely, if C is a cupola and fx and gy are the marginal, respective marginal, then hxy is the cupola function of these 2 reduced variate. So based on this property, this is basically from where we start entire application of this cupola theory, from that particular theorem. Here are again some of these examples are shown. Say, for example, this is the joint distribution for this domain, and with the marginals are fx is equals to this and fy equals to is this. So there always one cupola function do exist in this case. So what is this cupola function? That's the example problem here, and we can go for some quasi-inverse, and this u is equals to, if I just put this, so this quasi-inverse means when a function is just strictly increasing, and you know what is strictly increasing and what is increasing. So there we need to go for this quasi-inverse if it is increasing. If it is strictly increasing, then this quasi-inverse and inverse are same. So here, when we talk about this quasi-inverse, then for this function, this inverse function equals to 2u minus 1. If I just put that this fy is given as minus ln, so this is given in this in the problem itself, then this c is equals to that this joint distribution of their quasi-inverses. So these quasi-inverses, as I obtained from here, if I just put in this domain, then finally we will get one functional form of uv, where uv divided by u plus v minus uv. So this is the cupola function. Now this is slightly more, I should say that functionally more as compared to the independent cupola, where we can apply all these properties that we discussed so far just to check whether this is a valid cupola or not. And as I mentioned, that's quasi-inverse. Here it is mentioned, if any marginal distribution is strictly increasing function, then quasi-inverse is same as the inverse. However, if the marginal distributions are not strictly increasing, then the quasi-inverse is given by this properties that we have utilized in this previous problem. There are 2 measure of dependence, as I mentioned, that the scale-free measure of dependence. One is called the Kendall's correlation coefficient, which is related to the cupola function through this, but we can estimate the Kendall's tau from the data itself. Similarly, for the Spearman's correlation coefficient, that also we can estimate. And here the Kendall's tau, when we say, suppose that there are 2 variables x and y, and this is the pairwise data for them. Now, this paired sample of these 2 random variables x and y, there are 2 pairs are there. So if I just take the x1yi and xjyj, then they are known to be either of these 2 categories. One is called the concordant, other one is called the discordant. And there, when we say that concordant is that if xj is greater than xi and yj is greater than yi, or they are less both, then in both the cases, there this multiplication will be greater than 0. and in that case we call it as a concordant. In other words, when xi, yi to xj, yj, either both are increasing or both are decreasing, we call it concordant. But if one of them are increasing and other one is decreasing and vice versa, then this multiplication will be less than 0. Then we call it as a discordant. Now, out of this n paired sample, we count that how many such concordant pair and how many such discordant pairs are there. And if they are C and D, and the total number of possible these pairs that we can select, it is a n choose 2. And then this ratio is, we estimate this Kendall's tau from this expression. Similarly, for the Spearman's rho, which is the rank correlation coefficient, which is analogous to the correlation coefficient, except that instead of using the original values of the variable, we use the ranks. Once we rank them, that is xy, yi is replaced by their corresponding ranks, and then with using this rank, we calculate the correlation coefficient to get the Spearman's rho. It has a relationship, of course, between the two things. There is a specific group of copula which is known as Archimedean copula, and that Archimedean copula, again within the domain of this copula itself, if a function satisfied a property like this phi function is called the generator of the copula, and it's pseudo inverse of their summation of u and v. If it is equal to this copula function itself, we call that is an Archimedean copula. This can be proven for some of the Archimedean copulas theory, and this is how the generator function, there is a phi, is known as the generator function, which is defined in this way. That is, this pseudo inverse, as I called, is the inverse within the domain of this 0 to phi 0, and it is 0 if it is beyond that phi 0 to the infinity. For example, one example is also there. I am not explaining all the examples. So you can, I have already shared my slides. You can just have a look there. So this Archimedean copula, so far as the application in this hydrology, hydroclimatology is concerned, it is a bit more popular as compared to the others because it can be easily constructed. There are many varieties that are available, and they possesses nice properties. There is one example of this Clayton copula. This is known as, and depends on the how this this theta is basically the dependence parameter. So it can, so you can say that -1 to plus infinity except this 0. And how wide range of the dependence it can capture, it is shown here. One is the theta equals to -6, how this x and y will look like, and of course the reduced variate of this x and y. And if theta is equals to 5, then how they are look like, it is shown here. And another property of this, that Archimedean copula, in terms of its relation with the Kendall's tau, is through this generator function itself. So this tau we can estimate from the data from the sample that we have, and then we can put it in this expression to estimate this parameter of this copula, and then you can apply it once I identify that which one is there. So here are some of the examples, as I told at the very initially, that is the independent copula uv, just the multiplication of these two, and for this one the generator function is log t, that can be shown. There are Clayton, there are Frank, Ali Mikhail Hogg, Gammel Hogarth, Joe. These are some of the examples of the copulas that has been shown here. There is other group is also there, is called the elliptical copula, which is also utilized the multidimensional Gaussian copula, for which this is the joint distribution and these are the reduced variate. Similarly, there are some T copula is also there. As you can know that some of these copula we cannot have the closed form solution. We need to go for some numerical solution for this, for the application. And the one of the last part before I go to the second thing for its application is that there are, now we have the multiple options of this, exactly similar to the, for I have a data, I have multiple probability distribution, which is the best fit distribution that we ask for before we apply them. Similarly, for the copulas also we ask for the, which is the best fit copula for the data that we have. And in that case, what we have to, another new term is called the empirical copula, and in this empirical copula we can get that is the total number of data that we have, and we count that how many such values at which we are calculating the value of this empirical copula is less than this. This is just basically the counting, and this operator is just counts that if this is true, then it is equals to 1, if it is false, it is equals to 0. And once we add them up and get divided by 2n, we get the value of this empirical copula at the point u and v. So we have now two things. One is that called the empirical copula, and other one is called the copula which I can take from the distribution. So this superscript theta means it is the parametric copula, and here this one is the empirical copula which is coming from the data itself. Now, as you can understand that if these two values are very close to each other, then we are saying that is a better the fit. So one is from the parametric copula, the other one is from the data, which is empirical copula. Now, again, to measure the how close they are, there are two terms. One is the statistics SN. It is basically the difference and then square them up and sum them up. Another one is just their absolute difference. So difference between these two multiplied by square root n and take the mod and then take the maximum of this one, which is analogous to again that's why you know that this Kolmogorov's mean of statistics that we utilize for the probability distribution also. So this is called the TN. So lower the values of this SNTN, there are other criteria are also there. The better the fit is, so we can pick up the best copula from that. So I'm now gradually going to the second part where I'll try to give you some ideas about the application of hydrology and hydroclimatology. But in this part, in the very first part, I'll just try to show you what are the different applications that it can be possible. And other one, when I just take, I basically mostly discuss about the problems there, the associated variables. So the discussion, so far as the application is concerned, it may sound that more towards the real life problems that we handle, and there will be some part where I just utilize the word, okay, copula is utilized here to find out their joint distribution. So this is how we will proceed, and then we'll see that how it is there. So as I mentioned that there could be many applications, that it starts from the data generation, multivariate frequency analysis, probabilistic prediction of the hydroclimatic variables, and many other applications is possible. The data generation using the copula that preserves the dependent structure between the associated variables. So this is one of the things. So when we in the univariate domain, you have seen that we preserve the property of the probability distribution of a data before we generate it either in the Monte Carlo simulation and all that we do. But in this case, what we have to do when we talk about the more than one random variable, so their dependent structure has to be preserved. So there are two methods exist. One is that this specific to the Archimedean copula. So as I told that if we can somehow prove that it follows one of the Archimedean copula, then it becomes a little bit easier. And but there are some other general method for any copulas as well. So for a specific Archimedean copula, for which, as you know, that there is a generator function will be there, and we calculate these three terms part. One is this that quasi-inverse, then its derivative, and the quasi-inverse of the derivative. So these three things we calculate first. Then two independent uniformly distributed numbers, that is u and is generated, u from this u01, and you know that how to generate this uniformly distributed number. So once we create two numbers, of course they are not related to each other. Let us designate them as a number of u and r, and then we get two new variables s and w following these two relationship. And then since these are coming from their the generator function of some form of this generator function, the another variable v is obtained from this this relationship. Now that this new pair, one is that u and other one, the u is the originally that we have generated, and we have taken the other variables to reach the variable v. So originally u and generated v, these two are the desired pair of this random variable, which is I generated, but I maintain their dependent structure. The general methodology for any copula is that when we have selected this copula, then we take the partial derivative with respect to one, and it is basically giving the conditional distribution. That is, conditional distribution means the conditional distribution of v, one of them, conditions on that u equals to a specific value. Now we get this derivative and put this value, put the value of u equals to u, and whatever the value v we get the other one, which is basically much more general, as you can see, and is applicable for any variable. And from there we can just create one variable u, feed it in this equation, and get the value of v, and in this way u and v are the generated pairs. Next application, the general application comes as the probabilistic prediction, and there are, of course, depending on the problem that at hand, it varies from one problem to another one. But in general, the method that we follow is that we first of all estimate the marginal density. We estimate the scale-free measure of association, as I mentioned, there is a Kendall's tau. From there, we estimate the dependence parameter for different copulas. So once I get this one, this Kendall's tau is related to the parameter of the copula. For different copulas, different relation is there. So I have, say, for example, couple of copula function at hand, and of course we have to check it. So once I get that estimate, then we fit this copula, preserving the dependent structure among the random variables and estimation of this goodness of fit statistics. So the goodness of fit statistics also we discussed, and then from these two information we select the best fit copula. Once we select the best fit, then we develop this joint distribution among the random variables that is associated with each other. Then we find out the conditional distribution of the dependent variable given the independent one, and then we apply this conditional distribution to find out the probabilistic prediction, and also the quantification of the associated uncertainty, because it comes in the form of a distribution. So we can also quantify that what is the confidence level of that estimation. Okay, as I told, those are the some of the general topic, and it varies from the one application to the another one. Now we'll go to some of the very specific application. So first one is the hydroclimatic prediction of Indian summer monsoon rainfall, and it is the new thing is that there is a time varying temporal networks are there. Earlier, what happens, we generally utilize some of the large scale indices, like now it is already in the media news that El Nino and Southern Oscillation, also the large scale circulation indices from the Indian Ocean, it is known as the Indian Ocean Dipole. So utilize them, we find out some relationship, and we establish them how for a long-term seasonal prediction it is being utilized. But you know that it also has been found that there is some changes are there. So if we just establish the relationship now, it varies over the time itself. So that leads to a fact that whether we can go for a time varying that relationship or not. So whatever the understanding that we have, and there are some literature is already available, well-established literatures are also there. Whatever the development and the understanding that we have developed, there are several cases of the failure in the prediction of ISMR that we have seen earlier. So the temporal variation in the predictor-predictant relationship is basically one of the key issues, and that basically creates sometimes the bottleneck for this type of large scale prediction. And the conditional dependence among the predictors shows that the necessity for the constant scrutiny and update of this model, that basically leads to the dynamic model or the time varying model and that kind of thing. So temporal evolution of the association or the linkage, that means that whatever, say for example, this large scale coupled oceanic atmospheric phenomena, we call it, ENSO is one of the example, whether those things are over the time are changing or not. So two large-scale coupled indices, oceanic atmospheric phenomena, that strongly influence the variability of Indian summer monsoon rainfall are, as I told, the El Nino Southern Oscillation and Equatorial Indian Ocean Oscillation, which is the atmospheric part of Indian Ocean Dipole. And these are basically connected, is called the hydroclimatic teleconnection. And the above and below normal summer monsoon rainfall from, say, many years we have seen, it is favorable and unfavorable phases of this climate thing. But the new thing is that whether it is a time invariant or the time varying concept has to be introduced. It is not only that ENSO and IOD, there are other large scale indices are also there all around the world, and they have been shown that to influence the large scale circulation indices. I'm not going into the details of this El Nino Southern Oscillation and how they are basically is a warming part of this the tropical specific ocean, and it's associated with the anomalous sea surface temperature as well as anomalous pressure of these two regions. Why I am discussing these things? Basically, when we are utilizing some of the variables, we should know two things. One is the background science, that why I am utilizing, what is the mechanism that it is influencing. In this case, that what is the mechanism and what are the variable, the measurement of the sensor that we have to utilize before I go for this Indian summer monsoon rainfall. So here you can see that there are different regions are there, Nino 1, 2, 3, 4, and there is a overlap region is called the Nino 3.4, and this is basically the best correlated with this Indian summer monsoon rainfall. And the 3 months running mean is known as the Oceanic Nino Index. Similarly, another one is called the Indian Ocean Dipole mode, which is again, it has a positive phase and the negative phase. In the positive phase, this side is warmer and the convective activity is more here, whereas it is reverse in a negative phase time. And during the positive phase, we generally get a heavy rain over this Indian subcontinent, and the reverse when it is in the negative phase. Now again, the atmospheric part of this Indian Ocean dipole is known as this Equatorial Indian Ocean Oscillation, and that is basically reflected in the wind pattern of this red box that we can see here. So it is defined as the oscillation between the two opposite states of the convection in this western zone and the eastern zone. And equatorial zonal wind index, it is considered as a measure of this, which is the negative of the anomaly of the zonal wind in this red zone. So negative, remember that it is a negative of the anomaly of zonal wind. So zonal wind means it is along the longitudes, and the negative means, so zonal winds are generally from the east to the west, that is easterly, and negative means from this side to this side. Why it is negative? Because then this index, if it is negative, that means this side the convective activity is more and it carries more moisture to the Indian subcontinent, and leading to a favorable condition for the monsoon. Now, coming to the issue that I was mentioning, whether it is the time invariant or the time variant. So once I develop this relationship, is it applicable for over the years that is to come, or this can changes over the time itself? So there are two issues are there. One is that you have to identify the most influencing predictor depending on the appropriate lag. So how much lag we have to consider. And secondly, the identifying the time varying nature of the predictor predictant association. This is one of the things. And the conditional independence among the predictors, that is, if I have considered one such lag, the other one need not be utilized. And it can be applicable for in the general cases also, some of the hydrological models. So if we have one of the particular information for one particular variable, I may or may not need to the other one. That is the overall concept of the conditional independence to variable. So here the question is, what about the time varying model for the prediction of the ISMR along with the uncertainty quantification? These are some of the data description from where this data has been obtained, and this is how. So here again, as the application of the cupola that we are talking about is the C-vine cupola approach is utilized, and this is how it looks. So what happens in most of the modeling strategy, once we identify there are some of the input variables are like this, and we inherently assume that all the variables have their influence on the target variable itself, and that kind of approach is called the saturated model. But it can be shown that there could be three different variables can be categorized in from the input pool. Some of them may be totally independent of what we are targeting, number one. Some of them have the direct influence like this, and some of them are conditionally independent, like the green variable here that we can see here. That means the information comes from this variable to this via, and then it comes here. That means if I have the information of this variable, I may ignore these ones for some of the practical applications. And these are which are the directly influencing my target, we call them as a parent variable. And then we use only the parent variable, and then we develop some their dependence and the conditional variable, and that comes from the C-vine cupola for this particular application. And again, so once I get this information, how long it can be valid. So that means if I have a sufficiently long time scale, then once I develop it and I try to apply it for some time, and then after I go for a shifting window and redo this exercise to find out whether the same influence of this input set is available, is there or not. So now the question is that how far we can go once we develop the model, and before I have to relook in my develop or the calibrated model. And this is what is called the optimum prediction horizon. So that means the how much I can utilize, and as you can understand, it depends on the how dynamic that particular system is. If the system is highly dynamic, then I cannot utilize it for long. It has to be it has to be updated more frequently. So this n, so after this n years, which how many times I can utilize it, that we have to calibrate, and that varies from the one application to the another one. There are some animations are shown. I can just skip this part, and how to identify those called the age exclusion devices from the saturated model. So and then we can find out, and we can find out from their age strength of the connections whether they are which one as the conditionally independent variables. Now, if I just show you some of the results of this one and compare it with this time invariant counterpart, then we can say that, as I told, that optimum recalibration interval, then that basically we have taken as an option for this 1 year to 10 years to find out that which one is giving me the best performance. And then we can clearly show that the 3 years should be the optimum horizon for which I can utilize the model, the calibrated model. So every 3 years I am supposed to relook about this model calibration for its effective utilizations. So this we can just conclude. So once we use these 3 years as a optimum recalibration interval, then so 1950 if we start, so just an example, so it goes up to 1979, and again the next calibration I have to do for the 53 to 82. So if there is any temporal variation over this, then I can identify from this one. And there are some ENSO and that their lags are there identified. This is one of the typical dependent structure, how it looks like, and this y is the target variable. And as you can see that this completely this sector, even if we have considered in the initial pool, we can say that this is independent of what we are targeting. This is one of the example of this one, like this for different target years, and there are different probabilistic models that have been developed. And as I told that over the time itself, this is a three-dimensional plot, how their influences are changing, and there is a statistical significance also. So if it is significant, how they are changing over the time, over the time span that has been shown here. The final take home from this particular study is that, so if I just compare now the time varying model and as its counterpart is the time invariant one, and it has been shown that it is as much as when we talk about this time invariant, and this time varying and invariant can be applicable for the other traditional approaches like the SVR, or that even for the cupola models also, the SVNIT, we can utilize either in the time varying concept or in the time invariant concept also. And it is as much as we have shown that the 64% of the more accuracy that has been obtained from this when we go for the this time varying concept of this Indian summer monsoon prediction. Okay, so next another one we'll just take up that is from the precipitation. Another one is from the drought part, and how to utilize this one, some of the application that we will show here. And as you know that this drought as a prolonged status of the water deficit, which is perceived as one of the most expensive thing, and some of the vagaries of these droughts are too much even to change the GDP of a country, particularly for a agricultural based economy country like India. And you all know that there are different types of droughts are there, called the meteorological drought, agricultural drought, hydrological and socioeconomic droughts are there. So you can take up one of them, some of the say that agricultural drought, which is basically depends on the soil moisture part. And here there is one index called the SPI, the Standardized Precipitation Index, that is being utilized. And there one of the variables is the vulnerability risk and their recovery rate so far as the soil moisture is concerned. It is called the reliability, resilience, and vulnerability, from which is basically there is a threshold, and it depends on the application again. And since we are talking about the soil moisture here, so threshold will be maybe the permanent wilting point will be a good threshold to identify. So if the soil moisture is above this threshold, then we say that it is a satisfactory stage, and similarly if it is below, we call it as an unsatisfactory or the failure stage. And and this is not only for the soil moisture, we can apply it for the some other system also, and we have to define some of the threshold which I should identify as a the satisfactory or not satisfactory stage. And there are three properties that we are calculating here. One is called the reliability, and which is basically the probability of the system that is in the satisfactory stage. So that means how many for a sufficiently long time series if we have. So what is the probability that it is in the satisfactory stage? So higher the value, better the condition is. Second thing is called the resilience. Resilience is a measure that indicates that even if it fails, after it fails, how quickly the system returns to the satisfactory stage. So there are two cases can happen. One is that it fails and it remains failed, so which is not the desirable case, in particularly in this permanent wilting point of this soil moisture for the crop production and all. So in that case, it is not the favorable one. So that property of a particular region through the soil moisture is reflected through their resilience, and it is just calculated from this. It is in the failure stage at the time steps t, and it goes to the success or the satisfactory stage at t+1. So how many times like this switching is happening, and over that how many times it is in the failure. And last one is called the vulnerability. So once it fails, how severe that failure properties are. So, and here it is a pairwise their relationship. There is a reliability and resilience, as I have shown there in the mathematically. They can be though it is nonlinear, but it can be related to each other. Whereas the vulnerability, reliability, and vulnerability, resilience, these two are having some sort of randomness there. So we picked out this vulnerability and the resilience, and which we can show that there could be a negative dependence. Here there is one copula that is called the placket copula, and here that placket copula has been utilized, and this is the functional form of that one. All the properties that we discussed that may be there, it is we can check that. This is the parameter of this copula, that is the theta p, which you can calculate through this one, n00, n11, n10, and n01. Sorry, this is one of them are there. So it is basically that I just put for a particular value of point of uv in this way, two lines I just draw. So n00, that means that there are 4 quadrants are there, and I just literally I count the numbers in the 4 different quadrant if I take a specific pair of u and v, and for that pair I can calculate that what is these numbers and get this theta p from their mean values. And here in this particular application that we have show that this theta is basically 0.3471, which is shown here. Now the index that we have defined is called the drought management index, and this drought management index is defined in such a way that the probability of that the resilience is greater than a particular value and vulnerability less than certain particular value. So it is a shaded area in this case. So if I take any point RV, so that means the resilience greater than this and vulnerability less than this, both are basically if the resilience is high, then we say it is a favorable condition. If the vulnerability is less, we call it is a favorable condition. That's how the DMI is defined. And as you can see, it is a probabilistic measure. So it can vary between 0 and 1. And so higher the values, it is the more drought prone. And here there are 4 or 5 different points has been taken for already known region, how they are either from this northwest India or the northeast India and some part of this western Ghats. And we have seen that this is matching, these values are matching with this DMI. And there are some of the regions which are basically may turn out to be the similar so far as the only reliability is concerned, but if we take the vulnerability and resilience together, then the difference can be visible, particularly the C point that we are talking about, where that this DMI is 0.98 and this B1 0.177. one. So these two things can be seen from some of the published literature. So this is how we define this DMI, and then we find out how those things are changing over the time. And if it is changing over the time in the historical period, and then how that each of these 5 years duration, if we just considered, then for a particular region, what is the trend? So the slope of this linear trend, some part we have seen that, which has basically over the past, it has been shown that there are some part which is the trend is very high and some part is trend is low. We extended this analysis for this entire globe and for the future, taking the simulations from some of the GCMs, and we identified there are different domain-wise or the continent-wise, whether the drought propensities are, we call it as a drought propensity, whether they are increasing or decreasing or not. And the reds are basically showing an increasing, blues are showing the decreasing, and if there is no dots, that means it is the trend is insignificant. And here is some sort of that just for a overall continent wise how the continents are looks like so far the drought propensity in future is concerned. So just to find out the dependence between the resilience and the reliability, there to find out that joint distribution before we go for the their dot management index. So how that cupola function function was utilized. Another one, we come to the hydrological drought, which is here we have considered the stream flow as one of the variable, and here we find out the drought triggers. So drought triggers is the term that is defined as the pattern in the hydroclimatic variable that herald the upcoming drought. So the question is that is it possible to see some sort of signature in the hydroclimatic field so that we can say something that what is going to come up in the coming months? That's the overall thing of this. And as you know that there are different approaches are there. I'm just skipping a little bit. So there are two major goals are there. One is to model the joint distribution of the stream flow and the important the principal components of the precursors hydroclimatic variables. So as you know that there is a huge pool of this one, we go for a principal component analysis and find out some of the major components, and then we utilize those components to find out the joint distribution with respect with the stream flow and then we to test this cupola model for this capability to forecast the low stream flow that are more concerned so far as the hydrologic droughts are concerned. And the second one is to utilize this PCA cupola framework to develop the drought triggers information for a specific basin or not. These two are been taken from the two basins in Indiana, and this data, and there is a classification, as I can show is directly from here. So the classification starts from this D4 to W4 and how each and every months they are categorized as, and these color sets are basically showing the upper side is basically wet and the lower side is showing basically the dry part so far as the first water set is concerned. And similarly for the validation, the testing period, how they are whatever we how they are comparing with this observed and the predicted one, these two. There are here in this case we have utilized a 3 cupola that is called the nested cupola, and there are different categories we have utilized, and we have shown from their goodness of feet that the M6 was the best cupola in that. And then we identify, once we have identified and we got some confidence about their dependence, then we find out what could be, if I just categorize one drought category, is it possible to see what could be the possible status of this, the expected that principal components, and from there we identify the different types of these different variables initially that we have taken. For example, the soil moisture anomaly, temperature anomaly, precipitation, evaporation, sea level pressure, then wind speed, runoff. And we got a band or the information like this. So to read this one for a particular month, if I just see that these colors are basically different drought category, as you can see from this color bar, and so far as the soil moisture is concerned, it shows some sort of variability. So if it is related to this a domain, how is it? So we can say that the soil moisture, precipitation, and runoff, it gives some sort of sensitivity, whether the evaporation, temperature, sea level pressure, wind speed, it has a very less sensitivity. But there are two things. This is for the one, this is for the watershed 1, and this is for watershed 2, which are nearby to each other. Maybe the similar result has been got. One is that we have to, first of all, if we have these 7 variables only we considered, and out of which we have find out that these 3. Now, if one of them, the data may not be available for all the basins, then maybe the some other variable may pop up to be that more informative, I should say, so far as the to say something, to comment something on the upcoming drought status. So, the drought management index, that is one of the things that we have discussed, and then we have just seen that how we can utilize so far as the drought triggers are concerned. I'm not going the details of this one. There are few further readings are there for the participants if they want, and there are few tools, few statistical methods are there in this particular book. And these are some of the further readings, whatever we have covered here in today's thing. And let me stop here. If there are some questions, definitely please go ahead.
Thank you very much, sir. There are 1 or 2 quick questions. The first question is in the chat box, sir, that in probabilistic estimation of the parameters, slide 37, first step you mentioned was data pre-processing. My question here is, how much data length is required in terms of quantity in order to predict accurate?
The last part is the in terms of quantity in order to predict accurate. Yeah. Okay, fine. I think this is the question having multiple parts. So let me take the last part. In order to predict accurate. So as far as my knowledge is concerned, the accurate prediction is still not possible. I don't know that something that we can say exactly that what is going to happen, which is very, very difficult. But what you have rightly mentioned also, it depends on the multiple factors, and one of the factor is that data quality. So what data length is, that data length is one of them, is that what data length I should. So it depends on, it heavily depends on the which application that we are talking about. Most of the climate related studies that we talk about, it is the minimum, as you know, that for any climatological studies that we do, the minimum 30 to 35 years data is needed. But of course, the longer the data that we have, it is always better. And you have also mentioned the first step you mentioned was the data pre-processing. My question is the how much data length you can find. So far as the data length is concerned, as I told, that is a minimum requirement and depends on the which study that you are that you have undertaken. If it is the climate related studies or the impact related studies that you are talking about, minimum 30 to 35 years data is a must. Okay, and also, can I read that question?
Yeah, please, sir. Please, sir.
And also, I wanted to ask, can we predict the precipitation based on this approach? Yes, definitely. There are some work is already done. You can refer to that, and you can definitely utilize this one. But of course, one thing that you have to remember is it is not only for the precipitation. For any variable that you considered, what are the influencing variables? And that can vary over time, as I mentioned, as indicated in my talk, and it can also vary from over the space also. So that your association that you are trying to establish for a particular basin, say for example, the Western Ghats, may not be exactly same applicable if you are going to the northeast part of India. So those things has to be. There are some ways how to identify the what are the most influencing variable for a particular target. And here, as you have mentioned, precipitation is your target in that case.
Sir, one more question was there, that sir, in which unit vulnerability is measured here? The y-axis is 50, 60, 70, etc. And also the reduced vulnerability, which is 0.2, 0.4, 0.6, etc.
Okay, so here, so far as the vulnerability is concerned, in this particular application, initially how severe, that is the same as that the initial variable, that is the soil moisture, that was utilized. But when you go for the reduced variate, as you know that it is transformed through its marginal distribution, that will vary from the, it becomes unitless and it varies from the 0 to 1.
So thank you very much, sir, to explain such a complex subject in a simple way. Not only that, but explaining its application to hydrology, as well as spatial variation of parameters and predicting it. No, you have also shown the book as well as the relevant papers, which will definitely be useful to participants who wants to carry out work in this area. Thank you very much, sir. One thing I forgot to tell you all the participants, that when I have asked sir to deliver lecture, that time he agreed to deliver it. Later on, I received an email that he is down with COVID, and I am very happy to see that he is here today and he is delivering this lecture, though his health is not up to the mark. So I really thank you on behalf of all the participants, that your love towards academic only pushed you to deliver this lecture, even if your health is not good. Thank you very much, sir.
Thank you very much for inviting and giving me this opportunity to present in this good gathering. Thank you very much.
Sanjay, it was an extremely good lecture in spite of Rajiv